relation to the temperature, the people had to understand one of the important characteristic of a nature. What is the characteristic of a nature? If you have two systems, one system and one surrounding, when they come to close to communicate something, it is not a contact, I mean some way of communicating each other, the law of nature is they tend to reach equilibrium. They tend to reach close to each other. But many a times we have to live by not reaching equilibrium. The way I said it, no, I'm not interested in the human bodies most of the time struggle not to reach equilibrium with the environment, which are very strange, very hot, very cold. I don't want to reach. I want to cover. I want to open. I want to have a fan. I want to have an air conditioner. Suppose if the ambient temperatures are perfectly fine, I'll wear a minimum to look decent, but I don't stop the equilibrium deliberately. But what is required for a quantitative description is not to arrest the equilibrium, to follow the equilibrium. Any instrument, any measuring device which is to be developed to quantitatively describe a system, very important. Why I am using an instrument, why I am measuring something, it is very important to have a quantitative description. To have a quantitative description, I need an instrument. Unlike a general displacement length measurement, anything which is more powerful than the length requires a kind of equilibrium. So that's where the powerful law of measurement and essential for every law that is done in nature, engineering. So without this law, no, there can't be any engineering at all, you believe me or not. So this is the one, an universal law for measurement. Though this law states for a measurement of temperature, but actually this is a universal law for a measurement if you expand it. So today's my scope is to explain the zeroth law, the power of zeroth law, importance of the zeroth law, and also the openness in the zeroth law. That's what I say, no, the why thermodynamics is great is it is applicable to many applications. It's a vast, same way zeroth law has a vastness indirectly that I want to explain. So stating the zeroth law in a simple words, the zeroth law states that two thermodynamic systems in thermal equilibrium with the same environment are also in equilibrium with each other. The people say that when you are talking about the two bodies, why are you bringing a third body? The most of the times in a general engineering, though I have one thermometer, one body, and if I am trying to have a physical contact, you can't eliminate a third body of air gap or so. If the air gap is large and if the contact is perfect, this thermometer will read wrongly. Why? Because I ignored the fundamental fact that between the two systems there may be a third system environment which I want to avoid. If I cannot avoid an environment, no, better to have a good environment. That's how over a long time the entire medical sciences developed a powerful way of measuring the body temperature of a human. How did they do? When you go to the doctor, if you are grown enough, he will say open your mouth, lift the tongue, below the tongue I am keeping the thermometer. Why? Between the body and the thermometer, the environment is a good environment, a pool of environment which will encourage the equilibrium. So now, strictly speaking, the body's temperature is same as that pool of water or saliva. If you see, that saliva is in contact with the thermometer, and indirectly after measuring I said I have measured body temperature. Actually the doctor measured only saliva temperature. If the saliva temperature is far from the body, you are doing it wrong. So if I have a physical contact like this, for children they use a shoulder corner or some other novels are the ones. All these are very important. See the power of this. Though I am talking about system and surrounding, and I have to realize that most of the time between the system and surrounding there could be a third one. So that's how one need to be such a broad thinking to develop it. That's how you see this one on an average, even in a reality. In fact, this is not only the environment, it will be much broader, which I'll explain. So strictly speaking, I want A to be with the C. I don't want a B at all. Unfortunately, most of the practical cases, B cannot be eliminated. I've given you example. Now the thing is, strictly speaking, what is happening? B and C are in contact, are equilibrium, and A and B are equilibrium. But it is almost now physically impossible to have A and C to be intact. So instead of wasting your time putting lot of money, how to bring A and C, how to bring in a say, develop a thermometer which will suck everything, suck the air gap and stick to, that is all waste of money. In spite of that, you may or may not achieve, and try to create a good B and a helping B. So that is the power of this particular law. You can see this one, A can be at the most in equilibrium with the B. B will be in equilibrium with the C, obviously, because the saliva is a part of the body, continuously produced by the body. The B and C becoming equilibrium is natural. A and B can come to equilibrium very easily. You see the beauty. So that's how Zeroth law helps in quantification of any character economically. Otherwise, measurement of temperature will cost 2000 rupees for every patient, and nobody will depend upon such a thing. So you see the power of this particular law going ahead. Okay. So if A and C are in thermal equilibrium with, this is the Maxwell said in 1872. And this is the time already first law, second law were stated. Whenever people were trying to do some kind of engineering measurement calculations, there is no correlation between one lab to another lab. And there was a big misunderstanding between various labs, because nobody consciously realized the fundamental theory of measurement. They were trying to just touch or just do something. They thought they measured. It was not a perfect measurement. Why? The A was never in equilibrium with the C. They never thought about that. There is a big something coming in between A and C. And should I eliminate or should I promote? Or not only that, there are more things which are to be done for a perfection. Okay. So this is the one which led to a requirement. The Maxwell in 1872 stated in precisely, if A and C are in equilibrium with the B, and then A is in equilibrium with the C, though A can never reach C. I am giving you more and more in applications this one. So the practically this means that all the three are in equilibrium. Now, which says that another thing, always say that the system you know, the surrounding you know is what you know. There may be another surrounding coming in between your system and surrounding unknowingly. And you want body is to be the environment and thermometer to be the system. Yeah, body to be the system and thermometer to be the environment. Unfortunately, you cannot have only body and thermometer. There is something which is coming in between. So you respect that one. Now the thing is, if thermometer is a system, saliva is a environment. If the saliva is a system, body is the environment. If the body is the system, saliva is environment. If the saliva is the environment, the system, and the body, thermometer is this. So perfectly all the three are together. At any time you think about two, but the three together giving. So this is the powerful way of perfect measurement. Though, so the practically this means, sorry, a basis for a comparison of effect of temperature. The basically what I am doing the effect of temperature on A, the effect of temperature on B, the effect of temperature on C. So I only compare the effect of temperature. What is the effect of temperature on a thermometer? Volume expansion. What is the effect of temperature on my body? I am developing so many disadvantages. I may be feeling weak. I am not able to get a good diet. Many problems. All these problems are effect of temperature. Similarly, saliva has its own effect. So when I compare all the three effects, I am comparing only the effect of temperature, but I'll say I have compared the temperatures. Strictly speaking, what is temperature? Who knows what is the temperature? Unless the mercury rises in the thermometer, I don't know that there is a temperature. Okay, so the effect of temperature is the one which I am comparing. So whenever you are measuring the effect of a parameter, not the parameter, you have to be very, very careful that the effect is perfectly understood. Okay, so this is where the more and more deeper and understanding of this particular thing is required. You see this one, the unfortunate thing, the law which was stated formally in 1872 by the Maxwell, strictly speaking, it was invented very early, nearly 100 years back, by this great Scottish physicist who does a lot of experiments in his chemistry lab. And nobody considered this as a thermodynamics. Why? He was a chemistry professor. People thought that thermodynamics is different and chemistry is different. But what you need to is thermodynamics is a universal subject. There is no subject which will not say thermodynamics is not my cup of tea or my area. So because of that, 100 years, one theory which was lying. This is one reason. Another reason was this professor used in his class notes, he taught in his class, he never published this one. Later when the people were digging a class notes or him, then they found that. Very, very important. Law which was stated so early by this particular person never came into limelight, and because of which lot of mishappenings, wrong measurements, wrong decisions. I don't know how many things should have happened. This is one of the powerful lesson in the thermodynamics, that whenever you start your learning, you learn in a proper order. Step-by-step order. Don't ignore. Zeroth law I can learn anytime. It is so easy. Let me compare all the things and come back. That is foolish. Whatever your learning happened will be almost nullified. So this is the one. Sequentially developing a research is essential. A sequential quantification of a knowledge is also essential. Otherwise, we'll pay for it. So that's how. Now you see this one. The moment we depend upon the zeroth law, so entire 17th and 18th century, only way of measuring the temperature is by measuring the effect of temperature on volume expansion. And this volume expansion was physically visible for my eyes, because my eyes can easily distinguish the physical length. So that's how people made a very good quality of glasses, more visibility. On the glass, they have made some kind of comparison. Now the question is, how much rise in thermometer is how many degrees? How do I do this? So this is not the truth. Volumetric expansion will happen at any temperature. Now how do I do? The people started looking for some way of quantifying this one. So a volume expansion also qualitative. It is increasing or decreasing. How to turn into the quantitative? The people did a beautiful way. What is this one? You make a thermometer and fill with the mercury or alcohol and keep the entire thermometer in a ice. Yeah, ice water mixture. Then you will get some volume, some column rising in the thermometer. Let us say that is this particular point. Okay. Then you boil the water till it steams in an open environment and keep the same thermometer again, then you will get the topmost. Now I am happy. When I repeat again and again this one, it is coming back to the same point. When I repeat again and again in the steam, it is coming to the same point. At least I am sure that one minima consistently coming, one maxima consistently coming. Between the minima and maxima, I know the length. This length, I know how to give the number 1 mm, 2 mm, 100 mm, 20 mm. So now the thing is, there is a minimum which is 100 mm below the maximum. Now what can I do? Because I can measure each mm correctly, now I'll divide 0 to some 100 mm. That's how 1 degree, 2 degrees, 3 degrees. What could be the scale? That is up to the inventor. If it is a Celsius, named after Celsius. If it was a Fahrenheit, who divided into 180, then we gave a Fahrenheit. Something. That is the thing. But very important. Now the question is, you carefully study this particular one. What is naturally happening is, at some temperature, water freezes and makes ice. At one temperature, water starts boiling and producing a steam. These particular temperatures are naturally getting repeated. But I made a thermometer. Now when the thermometer is in thermal equilibrium with the ice, then there is a minimum rise of the mercury. Suppose if the thermometer doesn't reach equilibrium, and if it is not at all equilibrium with this, then what will happen? I wrongly predict the minima. So what is important? Why consistently same minima is coming? The people understood that, or people waited that, people constructed the thermometer that thermometer should reach in equilibrium with the ice water mixture. Why I am getting the steam point consistently again and again? Not only that, nature created a constant point, but I need to develop a thing, because I developed a thermometer which will reach in equilibrium, and I waited till it reaches equilibrium perhaps. So that's how I got it. The moment I know, I'll use this one. So people felt that this is not enough. In a modern world, I'm computerizing everything. I'm taking the decisions automatically. Suppose if I depend on this mercury column, every time one should look into. So how to make it more powerful? Then the people understood. So every time people did a research. What is the research? There are so many branches of physics, or within the physics there is a big branch. What is the big branch? Thermophysics. What is the meaning of thermophysics? Understand about the material in various way, how the temperature is going to affect the material behavior. You have so many thermophysical properties. What is that one? The resistance, electrical resistance of any material changes with the temperature, one physics. And somebody said there is another thing about this, there are so many things. At the end of the day, the people thought that why there is a one color to the any bulb? Because it is at one temperature. If the color changes, wavelength changes, why? The temperature is changing and another color. Even the color is also a function of temperature. Means you can find many things. Now how do I classify? One of such a powerful thermophysics which is ruling the engineering world nowadays abundantly, and perhaps you know the powerful thermophysical effect, what is called a Seebeck effect. So because of Seebeck effect, people developed a thermocouples. What is the thermocouples? You take a two dissimilar materials of your choice or a better choice, and you make a junction between these two, something like this, and you subject it to the temperature. I'm not explaining the thermophysical effect of like this. Then automatically there is a DC voltage which is developed. Now see the beauty. If this voltage can be transmitted to kilometers, and that can be digitized, stored in a computer, and the computer code will understand these digits and try to control the system. Now the question is, how many millivolts is 0 degree? How many millivolts is that steam point? How do I know? Now I need to have a thermal equilibrium between these two. So in order to know how many millivolts is equal to 0 of ice point or a ice point, how many millivolts is the steam point, again I need to have a kind of equilibrium. Now what is this? See this beauty? Because I understood a lot about the volume expansion. Now the volume expansion is A and the ice water mixture is B. But I want to, now I invented a new thermometer using a thermophysical effect called a Seebeck effect. Now this is C. Now the A and C should be same. They should be together. The A should will tell the C point, is it 0 or is it 50 or is it 100. Now in between I need a ice water mixture. In between I need a hot water, steaming water or so. Means in order to know the quantification of the Seebeck effect in terms of temperature, again I need the zeroth law. Why? I need to create an environment. This environment is an environment to the system A, system B. And A will be in equilibrium with the water ice mixture, and B is also equilibrium with the water ice mixture, but I can never get A and B together becoming equilibrium. That is impossible. How can I have a contact of thermometer with the thermocouple, perfect equilibrium? Impossible. And how do I vary the condition? Impossible. So see, the zeroth law helps in making many. Not only that, the people used the zeroth law to create various thermocouples. What is the various thermocouples you imagine? So see the beauty of this one. The people created what is called a grounded thermocouple. The what is called insulated junction. Now the biggest point is this. So I want this particular junction to be in equilibrium with the ice water mixture or a steam. But because of which what I am getting a current through this one. Suppose if the water is conducting, liquid is conducting, what will happen? Short circuiting. And suppose if I am electrically heating the everything, or then there is a problem. So that's why I should insulate the junction. Suppose if I electrically insulate it, what will happen to the equilibrium? So it is as good as I am going in a cold weather. Without a jacket, I can reach equilibrium very early. I'll start shivering. That is unreasonable. I don't want to have it at all. Then for that one, what I am doing to save myself, I am wearing a jacket. If I wear the jacket, what I am doing? I am troubling the equilibrium. This particular instrument has to reach equilibrium. But reaching equilibrium is leading to the short circuiting electricity. Then I put an insulation. Unfortunately, bad insulator of electricity is bad insulator of heat also. Now I need to do something more. Now you see this one, the people created so many varieties. Why? Want to reach equilibrium as early as possible. So the zeroth law not only talks about, not only used as whether I have reached our equilibrium or not. So zeroth law helps it. You design the instrument, you use the instrument, or you use the procedure such that the instrument comes to equilibrium as early as possible. There is a high level of utilization. That's why now there are so many thermometers. Why so many thermometers? Depending on application, in some cases, suppose if I go to the doctor, doctor can wait for 2 minutes to measure the temperature. Suppose there is an explosion of a bomb or so. Let us say we have a fire alarms in this room or in your room. And if there is a fire, they have to sense immediately. I cannot wait कि 2 minutes में equilibrium आ जाऊंगा तभी बजूंगा. Then by that time everything will get burned. So I can't give a more time. You see the power. This particular alarm or a sensor should reach equilibrium as early as possible. Why? Because by the time it reaches, if that particular danger grows, then what is the point in quantifying? Everything exploded, everything burned. What is the use of knowing anything? So that's how the powerful. That's why I'm spending more time on those topics which general textbook or a teacher is not spending. And because of which now we are lagging behind the invention research across the globe. These are the things which are very powerful to understand. Small statements, massive implications. If I do 10 years more research, if I start talking the same topic, I may say something more than what I'm saying now. Why? I've understood more than what I experience. So that's where. So very important. The zeroth law indirectly giving a clue and asking you to develop more and more alternatives, because many a times no, it is not the number I am important. Now, how long it takes to get a number? Most of the cases, I cannot wait for measurement to be 2 days, 3 days, or 5 minutes, even 1 second sometimes. If I want to know the danger or something else which will create a catastrophic changes. So that's how the zeroth law inherently says how fast you can reach the equilibrium also. Now you see, now I constructed a system. In my system now, there is an environment and system together. So what actually I have is some kind of ice water mixture to start with. But inside which now I already plugged the thermometer. Now because this thermometer is in equilibrium with the ice water mixture, for me this entire thing is a system. Okay, why? Because mere ice water mixture, no, it doesn't have the ability to quantitatively describe. You imagine, if I take a ice water mixture, I can touch and say, oh, it's a chilling here. Nothing else. Suppose if I have my ice water mixture along with the thermometer, oh, it is chilling at -3. It is chilling at -4, or it is chilling at 0. So that's how, by making this one, now I can say that this is a system with this temperature. Why? Already thermometer is in equilibrium. Now for me, this entire thermometer and ice water mixture is a system. Whatever shown by this thermometer is a system temperature. I don't have any doubt. Why? They are together for so long. They are in equilibrium. They cannot be in equilibrium at all, because I designed, I manipulated, or I constructed that they better behave like a equilibrium together. I don't allow. Now afterwards what I'll do, now I want to measure the temperature, which is more powerful way, that is thermophysical effect, which will generate electricity. I'll get a digital display. Not only that, that digital data I can transfer it to computer. Now the computer can think faster than me and buzz alarms much faster. So sometimes if I see something warm, I'll take 2 minutes to know that everything is burning around then. Why? I got a cold. My noses are not smelling the smell. So till that comes and burns me, I'm not alerting. Then what will happen? By the time danger will be high. Can I develop another sensor which will immediately digitize a small change and buzz an alarm that there is something happening? This kind of temperatures are not allowed in this computer lab. Whatever may be the computers, whatever may be the number of computers, it is unreasonable that this temperature can occur. There must be danger. Whine, it will buzz. You need to have alternate decisions. That's why what I'll do, I'm going to do this one. Now, this fellow should not misunderstand a problem and wrongly give a signal. When will that happen? Whatever this shows this fellow, shown by this particular thermocouple should be perfectly as per the system's behavior. So whatever sensor I am having this particular lab, there are many fire alarms, maybe in your lab also. This fire alarm should reach the equilibrium to the room immediately. Then only I can say that the signal given by the fire alarm is correct. If the fire alarm senses some nonsense and start buzzing, I cannot depend upon that one at all. It goes to a wrong signal. And afterwards, when it actually buzzes also, I don't care. Yeah, this is a wrong thing. It got corrupted. Its signals are unbelievable. Don't believe on this. Very important. Quantitative description has to be reliable. It has to happen with the highest level of confidence between the system and surrounding. Otherwise, what will happen? I am reminded of a small story come joke all of you might have heard about. There was one father who is a shepherd person and he has a naughty child. This first time he took the naughty child to the forest to graze the entire sheep which they have, herd of sheep. So this naughty boy was going in a different direction. Then father had to go in different direction because enough food was not available. He alerted him, there are tigers in this forest, be careful. And whenever you see a tiger, give me a signal. Then I'll come and save you and the herd because I know the techniques how to get saved from the tiger. So this boy is a naughty. He want to unnecessarily test it. And all of you know, first time he says, he gives a buzz. Then the father comes running and there was nothing. Second time also he misplayed. The third time he actually gave an alarm and the father didn't come because I don't believe this alarm. Now the case is that reaching equilibrium is developing a confidence between the system and surrounding. If there is a signal which comes without reaching an equilibrium, that confidence level is gone. That instrument I don't believe and I may have the danger. Very, very important to understand this particular concept very easily. Okay, now for a time being I am removing this one because I have my system with a quantification, like a thermometer is a part of my system. Now I know the instantaneous temperature of this particular system. Let me say the TS. S stands for the system. And this system temperature can change because here I am not arresting. The ice and water mixture is much hotter than the ambient condition. Because of the heat transfer, the ice will melt, everything will become a water, then the totally water will warm up and the process will freeze when this reaches equilibrium with the room temperature, isn't it? Even not only that, the system is changing, even the room also responds. What is the response? On the surface of this particular beaker there is a condensation. Why? The air which is close to this one will try to reach equilibrium again. And whenever the air temperature decreases, its capability to hold the moisture will decrease. That's how there will be small precipitation all around this particular thing. You see, everything is trying to reach an equilibrium. Okay, because of this one, the system is changing its behavior. I want to understand how this system is changing because I want a fast responding, fast reaching equilibrium. The time of equilibrium is the one. Okay, I'll go this one. The TS is called instantaneous temperature of the system. Then if I use a sensor, okay, so that is the temperature of the thermocouple. Okay, so the thermocouple is missing. Can you give me a pen for a while? In the document I want a pen. Yeah, no problem. Sorry, I'm using this. Acha. Okay, sorry. Okay. Now you see this one. Here I'm trying to draw the thermocouple because I missed that one in the. Okay. So what is the advantage of this one? This will give me the electric signal, digital millivolts, which can be connected to any kind of computer or so. Now this is the one which is called a temperature of the thermocouple. Now you see this one, the system is already changing its way and the thermocouple will have its the temperature. When will I believe thermocouple temperature is same as system temperature when they reach equilibrium? Now here is a big problem. System also changing with the time. Thermocouple also changing with the time. How can you believe? Suppose if the system thermocouple reaches very late and system is changing, then I don't know anything about the system. So that's how the Zeroth law talks about whenever the system behavior is changing with the time, then you need a more powerful sensors which will instantaneously reach equilibrium. So then no, I can say that changing temperatures can also be measured. Okay, so now you can see this particular thing. The TC is the instantaneous temperature of the thermocouple, and this is the one. So all of you will learn, these are called a first order systems. You may learn later this particular mathematics. I'm avoiding because many universities may not be interested in. It is very, very important to design the thermometer to reach or to satisfy the zeroth law as early as possible. For that one, you need to know one of the fundamental conservation of energy. What is that conservation of energy which gives this equation? So if in a small duration of time, because I suddenly immerse and small duration of the time, this is what is going to have. The heat input to the thermocouple will be used as change in energy of the thermocouple. And there is a continuously the heat transfer from the water mixture into the surrounding. And I need to believe this one only when the system and surroundings reach equilibrium. Now you see this one. There are some few things. This is refers to the response of the thermometer. If this rho Vc is very large, no, it will very slow to reach the equilibrium. Similarly, this is the one I said it. No, you cannot eliminate the environment in between. So there are many points. Perhaps it goes beyond the syllabus. But what I want to say from this particular theory is the power of zeroth law is to develop a fast responding also. How the fast? You see this one. Let us say I have the system temperature constant. Okay, that's why you are going to a doctor with a high fever. Your body temperature is almost constant. Now the doctor keeps the thermocouple in your mouth and he has to wait for some time. Why? This thermocouple is first time in contact with the body. It cannot immediately show. Now you see this one, slowly the effect of temperature on the instrument is increasing. Suppose if the doctor is in a hurry because there are too many patients, let me finish. If he doesn't wait for a time, what will happen? He is measuring only this much. If he waits for some more time, it is more close to the truth. He actually thinks typhoid, it may be malaria, because he doesn't get the correct temperature, correct symptom, or there could be anything else. A high fever can be concluded as a mild fever and there will be a problem. You see this one. When you see the system behavior, there is a particular way system behaves. I wait for some time, t, time period, I'll get some change. If I wait for double that this time, I'm getting another one. I'm waiting for so long, even then it is changing. How long I should wait? Should I waste all my time only for waiting and not taking a decision? So that's how zeroth law talks about the feasibility of a zeroth law. A given instrument is designed for reaching equilibrium or it is a nonsense. You don't know how to create. What is the best thermometer? The best thermometer is the one, this 4T is less than a second. A 4T should be less than a minute. Some applications 4T should be less than a millisecond. Means within a millisecond, the thermometer is 98% close to the system. Only error is 2%. 2% error I can tolerate. Okay, and suppose if it takes a 1 hour to reach 98% close, no doctor will measure correctly because he cannot spend 1 hour per patient and lose all his earnings. So very important to design a thermometer. You see that is so much depth in the entire thing. So that's where whenever you are designing this T, time depends upon the density of the material, the volume of the bulb, thermal capacity of this one, and also the environment. If the environment is air, it is very long time. The environment is a pool of saliva, the T will be very small. Why? The heat transfer coefficient is very high for the saliva and ordinary air is very poor. Maybe it is more for you at this point of time, but I'll go ahead with this particular thing. So the demonstration of zeroth law in a perfect way. You see this one, I have a brass, a hot brass block, hot a copper block. Then what I'm doing, I'm using a thermometer. So this thermometer is not in equilibrium with either brass or a, now you see thermometer is not at all equilibrium with either of the one. But I want to know brass temperature and copper temperature, are they same? Are they different or so? Then what I'll do? Then I'll take this thermometer and keep it in contact with the brass. Then automatically what will happen? There is a signal coming. What is the signal? Mercury level increasing to this particular point. Now I draw a line. And now I'll take this particular thermometer and have in equilibrium with the copper. Suppose if this level is perfectly equal to this one, I'll say the brass is at the same temperature of the copper. Otherwise, I cannot compare the brass and copper just by the human touch or so. So quantitatively, I compared. This is the one which is called a thermal equilibrium. The temperature with a third body, they in turn have the equality of the temperature. They are in equilibrium with the third body. So the thermometer is in same temperature with the copper. The same thermometer is also in equilibrium with the brass, and hence I can say brass temperature is same as the copper. Yeah, brass will obviously in equilibrium without touching. Now the brass never will touch copper, not required at all. Why? I cannot have the brass and copper touching at all. I don't want. But I still want whether the brass and the copper are the same temperature or not without touching. Now without touching, because the zeroth law says, now who is AB? A is a brass, B is a copper, C is the thermometer. Now initially A was in equilibrium with the brass, the later the same thermometer is in equilibrium with the copper, but the effect of this one is same because the same line, same rise. So they are in equilibrium, equality of the temperatures coming naturally. Okay. Where? You touch it. No, I've been telling you the without zeroth law, there is no thermodynamics, no temperature measurement at all. So thermometer is showing a reading. That reading is reliable if and only if thermometer is in equilibrium with the body. Okay. Suppose if the thermometer never reaches equilibrium, then there cannot be any measurement of the body. But the biggest problem is thermometer can never touch the body directly. In between there has to be an environment called a saliva pool. If the zeroth law is not required and A is the human or a patient, B is the thermometer, you try to touch it, then you will never reach equilibrium so easily. I can touch anywhere and measure the temperature, but unfortunately I cannot touch any part. Why? I need to respect that there is an intermediate system which is disturbing the A and B. And there is a C entering into. If I don't create a C which is encouraging the measurement, all the measurements made by the thermometer is stupid, useless. Very important. Every time when you use the thermometer, A, B, C are always there. Not only that, and how do you get the readings on the thermometer? Who made the readings? Because this thermometer was compared with another thermometer which is maintained by a Bureau of Indian Standards, and they together. Means whenever I measure the temperature with this thermometer, because this was in equilibrium with another standard thermometer, I believe that if it shows 20, it is 20. If it shows 40, it is 40. This thermometer was made to be in equilibrium. So every measurement has to be in equilibrium. When it is a temperature, it is a thermal equilibrium. Otherwise, anything else. There can't be a measurement at all without understanding a zeroth law. The second one is the time constant you have mentioned is only valid for particle? No. See, the expression for the time constant which I have given is valid for any thermometer, but you need to know what is the corresponding density, corresponding volume, corresponding specific heat, and corresponding heat transfer coefficient. But otherwise, any kind of temperature measurement, this is how the time constant will decide primarily. And only the thing is you need to know appropriate words or appropriately measuring the rho V and C. That's all. But otherwise, it is reasonably generalized, unless system is a higher order, which I'm avoiding for a time being. So I was telling you the again and again, thermometer coming in equilibrium with the body is a notional. There is an environment between the two always. This is one point. Okay, so I go to a market and buy a thermometer, isn't it? And who made a scale on this thermometer? By comparing this thermometer with a standard thermometer in a Bureau of Indian Standards, which is made with a very high precision. Means this thermometer was in equilibrium with some thermometer. Now I am using this thermometer to measure my body temperature. Means unknowingly this thermometer was in equilibrium with another. So every time, what I am saying now, whenever you are measuring a temperature, this ABC many comes into, not even a single ABC, one set of ABC. So without Zeroth law, there can't be a thermometer made at all. First, a thermometer is made. What is the meaning of thermometer? If thermometer is A, it was compared with the thermometer B. Now this thermometer is used to measure the temperature of me, who I am C. Now you see, the B thermometer was in equilibrium with the A when it was made. This B thermometer is in equilibrium with the C to measure me. Means my body temperature is as correct as somebody who measured in a laboratory. That's why somebody makes a medicine in America, whenever your body temperature is this much, you should take this medicine. Did he measure your body temperature? But the medicine was given, but this body temperature, this is the medicine. This doctor measures with another instrument and goes to the booklet and takes that medicine. That medicine was never based on your body temperature. That was done separately. This was done separately. How come I'm believing that whatever he measured is also same? Because inherently the whole scientific community is strictly following Zeroth law. Zeroth law. He has measured 100 times. Whenever the body temperature is like this medicine was working. And that thermometer was different. The patients whom he measured to develop the medicine was different. But I am using. But inherently, there is a confidence level that everywhere there is an equilibrium works. And this thermometer was inherently equilibrium with something which was used by the developer or a inventor of the medicine. So this temperature is equal to this patient temperature, and hence this medicine will work. In fact, no, if I go on telling, the deeper and deeper consequence, without Zeroth law, impossible for decision making at all. Okay. You be more focused. You think that at a given time now you are only looking at two, thermometer and patient. And unless you are a visionary, you cannot develop the third body. If you don't realize the third body, then gone. You can never make a good instrument. You can never use the instrument correctly. Very important. Whatever you see is not the truth. The truth is much more complex than what do you see. Very, very important. While measuring the temperature, always Zeroth law powerfully acting many ways. Not only that, if this thermometer takes, doctor waits 1 hour, still increasing, what he says, ye to kharab ho gaya, throw it and take a new thermometer. It is not readily reaching equilibrium. Any thermometer not reaching an equilibrium for more than 2 minutes is a stupid one. You see that to qualify an instrument also Zeroth law. Very important. Equilibrium Zeroth law is a fundamental to measuring the any temperature. ABC always there. If you see, if you think there are ABC, if you ignore, you think there is only A and B and mess up everything. You can never come up with the right thing. Okay, so that is the one. Finally, Zeroth law is if the substance that composes the system in thermal equilibrium and the temperature will be same throughout the entire system, and we may speak of temperature as the property of system. Very important. If the within the body temperature varies, then you cannot say that this is the temperature of the body. Now you can say that the locally thermometer is in equilibrium with only this part. Another part is having some other temperature. So very important. Zeroth law talks about the uniformity of temperature of a body, not human, many things also. Very important. Only in this part, this thermometer is in equilibrium. When I change this one, same body, another part, the equilibrium condition is changing. Means The body temperature is not uniform. Very important. So it says many things more and more deeper. So if I extend it, no, I can extrapolate it. Unfortunately, zeroth law doesn't talk about any other equilibrium. Zeroth law only talks about the thermal equilibrium. That is enough for us. We can develop a modified zeroth law for pressure measurement or a force measurement. Let us say I have one LPG cylinder, one oxygen cylinder. I want to know whether they will be in equilibrium or not when I connect it. Otherwise there will be explosion or anything. If I don't match the pressures, there will be explosion. More oxygen, less LPG, more LPG, less oxygen, not able to burn, there will be burst. Now what can I do? I'll take a known B. Okay. So now A and C. Now what I do? I put this pressure gauge, and this pressure gauge eventually will come equilibrium with the LPG the moment I contact, mechanical contact. Then I'll note down this reading. Then take this particular pressure gauge and compare with the second one. Now you see, if that equilibrium position is same, then I can say LPG is in mechanical equilibrium with the oxygen cylinder, means both have same pressure or both will apply same force on a given area, whatever way you want to use it. Now you see this particular thing. So when two bodies have the equality of the pressures with the third body, okay, they in turn will have equality of the pressures. Then I'll before connecting, I know that these are matching. Sometimes oxygen pressure cylinder is very high. Then you need to put some kind of a valve which will reduce the pressure. These are called pressure reducing valves. If the PRV fails, what will happen? Oxygen will come explosively. And LPG pressure is small, oxygen cylinder pressures are in general more. Before you connect, there should be a regulator which will change the oxygen pressure, and before they mix it, then they are perfect. How do you do that? With the gauge. There has to be a proper pressure gauge on the LPG line, on the oxygen line. In a big industry, they'll try to monitor every time. Otherwise, what will happen? Nothing can happen. You can have, see, this cannot be called zeroth law, but when there is a thermal equilibrium, that is the zeroth law, you can measure the temperature. When there is a mechanical equilibrium, it is an extension of zeroth law. That's why I am teaching something which is not taught in a regular, but it happens in every engineering. Then I can say that they are in mechanical equilibrium. The force, torque, or a pressure. There can be three different things. That is the beauty. That's why zeroth law doesn't talk about other equilibrium. When it comes to the thermal equilibrium, only the thing which is common is temperature. If I take 100 different thermal equilibriums, all thermal equilibriums talk about the equality of the temperature. But unfortunately, when I say mechanical equilibrium, sometimes pressure is same because pressure is similar. Sometimes force is same. There you cannot define even pressure. Sometimes in a rotational sector, the torque is same. But all are a mechanical equilibrium. So that's how the zeroth law talks about thermal equilibrium and leaves for the intelligence to talk about other equilibriums. So a mechanical equilibrium can occur when the pressure is same, or a force is same, or a torque is same. So that's how zeroth law doesn't talk about every equilibrium as a law. Why? There are many ways mechanical equilibrium can occur, but our thermal equilibrium occurs almost in a single way. So that's how there is a law which is you learn from the zeroth law, implement in the other parameters. You can measure the force, pressure, torque, or anything else which requires with the mechanical equilibrium. So now that's how when it comes to the mechanical equilibrium, there is a good amount of, any more questions? No? No. Okay. So that's why the zeroth law, very clever. The people are very interested. Whenever I talk about the zeroth law occurs in unique way. The possibility of occurrence of zeroth law is perfect, high degree of thing. But when I try to have a zeroth law for a mechanical equilibrium, then there is a confusion. First confusion, I said it same mechanical equilibrium, sometimes I am balancing the pressure, sometimes I am balancing the force, sometimes I am balancing the torque, or sometimes I may balance something else but which comes into the mechanical equilibrium. So that's how everybody should know what he is balancing. That's why the law cannot be stated when there are so many varieties possible. And not only that, there is another beauty of confusion when it comes to the mechanical equilibrium. You take the atmospheric air, the standstill air. The one layer of air is above the another layer is above the another layer. And if I take a glass of water, okay, and if I take the glass of water and on the top on the bottom, the water is equilibrium. The water is not moving. Can I say the pressure is same throughout? No. The dead weight is adding to it. Now see, sometimes no, the mechanical equilibrium occurs when the pressure varies according to the hydrodynamics or a Pascal law. If the force varies more than the law, then equilibrium will be disturbed. That's how no, mechanical equilibrium requires a lot of deeper understanding. Okay, you see this one. If a system is in mechanical equilibrium, there is no tendency for pressure at any point to change at a given point. But now you see this one, when the point becomes a bigger, and no doubt this water parcel is not at all moving, it is in equilibrium. But now I cannot say water at this point, the pressure is same. Though they are in equilibrium. Why? You need to apply a correction to hydrostatic pressure. So there will be a variation of pressure with elevation because of the influence of gravitational force. Suppose if I go into the space where there is no gravitational force at all, a point where, then perhaps no, mechanical equilibrium means that entire field is a uniformity of pressure. Because of the gravity, the mechanical equilibrium has to be corrected for something else. If the pressure varies according to the gravitational force or a hydrostatic force, even then the equilibrium is maintained. So a fluid is in equilibrium doesn't mean that everywhere pressure will be same in the direction of elevation, in the direction of the gravity. When I move normal to the gravity direction, then again mechanical equilibrium has to be satisfied. Wonderful way. So that's how no, the mechanical equilibrium has to be learned from a zeroth law. After understanding perfectly thermal equilibrium, then only you can talk about the mechanical equilibrium. In many thermodynamic problems, the variation in pressure with elevation is so small that it can be neglected. Suppose if I take the atmospheric pressure, because the density of the air is so small, even for a kilometer height now, I don't say that the pressure is changing much. Suppose if I take a water, even more than 2 meters of water, the pressure below is different from the pressure on the top, depending on the density. So you need to say everything. There is a conditional requirement. The last one is not only that, there are chemical equilibrium. You can see this chemical equilibrium. A system is in chemical equilibrium when there is no tendency for quantities of species to change. So now I have, see, most of the fire alarms are chemical sensors. What do they sense? They sense maybe CO2 or maybe some other chemical which occurs only when there is a fire. Now what happens? This particular sensor should come to equilibrium readily whenever there is a fire. Now actually most of the fire alarms nowadays are chemical sensors rather than a thermal sensors. Why? They are fast responding. Now when the species sensed by the sensor are in equilibrium with the system, then I can say they are in chemical equilibrium. Whatever sensor is saying is correct. So people extrapolate zeroth law beyond a mechanical. You see this one. When two bodies have the equality of concentration with a third body, then they are in the in turn equality of the concentration. So I can say sense sample A and sample B. Somebody says there is a food industry. The food industry, in order, when you are making some kind of eatable, you need to get what is the permission for agromark. What the agromark? Agromark will test the composition of the food with various sensors, and he'll get 100 samples or 50 samples or 10 samples with the producer. All the 10 samples should give within a range of composition. Otherwise, he will not get the agromark. Now, once he gets the agromark, he will go on producing that. Mera agromark hai, mine is as per the equilibrium. Now you see the sample which is tested by the testing authority, the sample I am eating are different. Why I am eating? Because that sample was in equilibrium with the one sensor. This food was made consistently with equilibrium with another sensor. So you see this one, ABCD chemical equilibrium. Then I say that this food, not only that, a company will not get a permanent agromark forever, annually or bi-monthly, depending on the policy, because these particular people may be initially showing something, afterwards neglecting. So you have to get the certificate, very important. A zeroth law talks about thermal equilibrium but gives ideas about more and more products, more and more engineering service. So that's how the thermodynamics talks about more equilibriums, not only thermal equilibrium. So that's how the chemical sensors are made. Now I'll give you, can we selectively detect a chemical? Okay, so what are you making? Can we detect the classes of chemicals? Within the chemicals, there is a class, there is a subclass. Okay, now an electronic tongue or a nose. Basically, we are developing electronic tongue or a nose, which will go in equilibrium. What is a thermometer? Thermometer is a electronic thermal device. Okay, touching, sense. This is a tongue or a nose which will taste it and come up with this entire thing. So the chemical senses covers a wide category of devices. Now you see this one, when the two systems are in thermal equilibrium, only the temperature is same. But when two chemical sensors are in equilibrium, there is no rule that it is CO2 same always. Sometimes oxygen is same, they are also in chemical equilibrium. Sometimes carbon dioxide is the same, they are in chemical equilibrium. A chemical equilibrium leads to equality of many other concentration. That's why you cannot state as a law. Zeroth law is such a universal, looks like a unique. Whenever there is a thermal equilibrium, it is only the temperatures which are equal. So easy. Whenever they are in mechanical equilibrium, not only the force, pressure may be equal, torque may be equal. There is a variety. When it comes to the chemical sensors, more obligations, more variety. Strictly speaking, ABC are in equilibrium in application 1. ABC are in chemical equilibrium with application 2. ABC are chemical equilibrium application 3. In application 1, it may be oxygen same. In application 2, it is the carbon dioxide same. In the application 3, it is the carbon monoxide same. But all are in chemical equilibrium. All are satisfying that equality ABC. But unfortunately, there cannot be a unique answer. When it is a thermal equilibrium, any number of applications only matching the temperature, degree of temperature. When it comes to the mechanical equilibrium, sometimes pressure, sometimes force, sometimes torque. When it comes to the chemical sensor, sometimes oxygen, sometimes CO2, but all I have, because of the variety, the people did not state a separate law for this. Why? Once you understand deeply zeroth law, you can develop all other equilibrium. At the end of the day, it is impossible to have a correct quantification of knowledge, correct quantitative description of a system unless you believe the equilibrium and zeroth law. You are basically learning the zeroth law, but may not be using the zeroth law. You are actually using some other law, but analogous to the zeroth law, because zeroth law talks about only thermal equilibrium, but in general you may be doing. That's how no, there is another equilibrium. So I'll skip these points. An application which so the finally there is what is called a thermodynamic equilibrium. Are we at the time? Okay, so I'll just say this particular point and leave, go to the next topic. You see this particular one. So when the system is in equilibrium regarding all possible changes of state, we say that that system is in a thermodynamic equilibrium. Zeroth law talks about only thermal equilibrium. Very careful, be very careful. But whenever I talk about equilibrium in thermodynamics, I am not only interested in a thermal. A thermodynamic equilibrium requires all known equilibriums. Okay, so it should be in a mechanical equilibrium, it should be in a thermal equilibrium, it should be in a chemical equilibrium, it should be in an electrical equilibrium or a magnetic equilibrium. Everything should be done. Very important. So the zeroth law talks about only thermal equilibrium, but gives an idea that similarly many equilibriums can be established. When it comes to the thermodynamic equilibrium of a system, there is nothing happening thermodynamically to the system means all possible equilibriums are achieved. I can say system is in thermodynamic equilibrium with the surroundings. If and only if thermal equilibrium, mechanical equilibrium, chemical equilibrium or any other equilibrium which is important to that particular thing. See this one. The breadth of thermodynamic equilibrium is much more than the zeroth law. Why zeroth law doesn't talk about other equilibrium? Because there are many possibilities for the same kind of equilibrium. So very important. Learning a zeroth law much deeper is essential to become a good engineer in your life. Not only electrical, not only mechanical, not only bio, every aspect of engineering is essential. Otherwise, you can never have your life very easily going on. Thank you. Any more questions? Oh. Yeah, no. Ask him. Okay. So very important. Don't think that thermometer measurement is a simple AB. Very dangerous. ABC you need to think. You need to establish. There are 100 ways a zeroth law is occurring when you are measuring a temperature. I give a few occasions like saliva in between or another environment in between. This thermometer was calibrated with another thermometer. There are small examples, but very important to convince your student and you yourself that measurement of temperature is impossible without zeroth law. And while measuring, you see only AB, but behind the screen, ABC, ABCD, ABCD, EF, anything can come. But any point of time, ABC, BCD, CDF, etc., going on. Thank you. I'll stop it for here, and we'll go to the most important topic next time. But I'll skip now the measurement of temperature, measurement of pressure, manometer construction, because many universities will have this syllabus. But I'll not discuss that one. I'll discuss something which is a very fundamental to be learning. Okay. So I'll not talk about the measurement of temperature, problem solving, manometers, design of manometers, use of manometers. That I'll not do because they are more obvious. Please teach on your own. If you have in syllabus manometers, thermometers, types of thermometers, their working principle, I'll not discuss that one. I'll go to the next theoretical and fundamental topic, which I'll tell you well before. Thank you.